So this is a bit of a payoff for all the work that you guys have done expressing the stuff that we know about coordinate systems in terms of tensors, because it turns out that the tensors are a really easy way of understanding the relativities. So expressing this grab bag of formulas that you may have learned about when you learned special relativity in terms of a single kind of unified set of tensor expressions and transformations. So this is what we have so far, is that we have a metric tensor. So this is the metric tensor for spherical polar coordinates. It's an orthogonal coordinate system, so we got zeros on the off diagonals, and really what this is the scale factors squared along the diagonals. And this thing can be used to express all of the vector calc formulas that we have so far. So this is what the divergence looks like for something whose metric tensor you know. And what you can also do is use it for its, in some sense, its primary purpose to express a little piece of actual physical distance. So if I have two little differential bits of a vector, they're contravariant, they got upstairs indices. In both here and here, we have Einstein summation. We've got an I downstairs and upstairs, j downstairs, upstairs. So this has an implied sum over I and j, and this has an implied sum over k. This is the actual distance that you travel. So if you were to try this with gij for spherical polar coordinates, you would get exactly what you think. You would get a dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Like an actual distance that you travel just expressed in spherical polar coordinates. And this is the nicest way of mathematically unifying the relativities again. So the first thing we have to do is get out of space and go into space-time. So the profound insight, I guess, is that Newton's idea that in some sense the universe was this kind of flat stage with like a big grandfather clock behind it, ticking relentlessly and uniformly is not correct, and that space and time are actually kind of a unified concept. And that what I should do is I should talk about events in space-time with a 4-vector. So this is a location in space-time, and it is the time, the x, the y, and the z coordinates, if we just want to kind of stick to Cartesian for now. We'll do non-Cartesian in a second. And yeah, I'm just saying t. I'm going to put the c in the metric. And again, the idea of special relativity, at least, is that if I abandon the independence of t and the spatial coordinates, for instance, the faster I go, the slower I seem to move in somebody else's coordinate system. So this can be expressed with a metric. So we're going to have a metric for special relativity, at least. And what our space-time metric is going to tell us, in some sense, is how fast or how far we've moved, not through space like we have here, but through space-time. And in special relativity, this has a traditional term. So nu, and we'll do, eta, mu nu. There is some degree of variability among scientists as to whether or not you put the minus sign here or you put 3 minus signs there. I kind of like the idea of putting the plus signs there, like a lot of people, because distances are positive in 1D, 2D, 3D, and then suddenly you go to space-time and distances are negative. It just doesn't make a lot of sense to me. But this is the metric, and the idea is that it runs over not just space, so that's this subset of it, but space-time. So in general, our Greek indices, mu and nu, will go in between 0, 1, 2, and 3 by convention. So 0 is the time coordinate, and then 1, 2, 3 is the space coordinate. And the thing that this lets us do is define, just like we did here, an interval. So that's space-time, this is the metric, and this is what's called the interval. And in some sense, it tells you how far you've moved, not through space, but through space-time. So we have eta mu nu, and then a little bit of distance, so call it dx. I like sticking with my notes. And this, again, is Einstein's summation. So we have a repeated index mu upstairs, downstairs, and nu upstairs, downstairs. So we have to sum over both mu and nu. And if I were to write this out using the metric, I would get exactly what you may have seen in your kind of non-tensor algebra-based special relativity introduction. And in some sense, what the whole deal with time dilation and length contraction is that this is always constant in any frame. So if I just stick to 1D, I get, I can express a graph like this, and I can talk about intervals in between events. So let's say I have two events here and here. This interval, ds, this is, or ds squared, and it seems so weird to have a squared thing be negative, but realize that's positive because we have a minus on the c squared. So this is a positive interval. This is what's called space-like. And in a space-like interval, this event and this event cannot affect one another, so these are causally independent. So we could have another interval, time-like interval, for which this is true. So for instance, this and this would be characterized by ds squared is negative, weird as that seems, squared negative. But again, that's because of the minus c. This is a time-like interval. And these two events can be causally connected. And then we have this kind of bizarre thing. If we're right along a 45-degree angle on a space and time diagram, space-time diagram, we have ds squared equals 0, and this is a null interval. Okay, so that's moving at the speed of light, essentially. So this lets us, the interval lets us actually diagnose whether or not things can be causally connected or not. If I'm just sitting on my couch and my friend is the observer also sitting on the couch, this is what I would look like to him if we're sitting on the same couch. I would be moving through time but not space. Right? Okay, so the idea behind, so a lot of zeros and a lot of like needless baggage, but this is where this becomes useful. I can define Lorentz transformations. And Lorentz transformations are the set of transformations that leave the interval unchanged. So they include two things, one of which we've already talked about before. They could just include normal spatial transformations. And we're going to call these things capital lambda mu nu. And this is one possible subset of the Lorentz transformations, which is we do nothing in time, and we just embed within this one of our allowed transformation matrices from, first day of class. Oops. I feel like I'm very backwards today. Okay, so just take a set of direction cosines embedded in this. We do nothing in space. So that is one of the subsets of Lorentz transformations. What we can also do is we can do what you guys did algebraically in your first introduction to special relativity, which is we can boost. And what this would be is the mathematical expression of me getting in a rocket ship and then increasing my speed. So relative to where I was in my pre-boosted frame, time might seem to go faster for the things I'm observing, and lengths might contract. So these also include boosts. And let's just boost in the x direction. Might look like this. with the usual definitions of beta defined as the fraction of the speed of light you're traveling at, and then gamma defined as 1 over the square root of 1 minus beta squared. So the thing that goes to infinity when you're moving at the speed of light. Okay, so incorporated in all of this is length contraction and time dilation. So this is basically all of those, again, grab bag of formulas that you learned kind of piecemeal. And so writing this out and referring to it the way that we talked about rotations and reflections early on in this class is you think that there is some event, or really this is an interval, right? So think about these as like deltas. It's going to be somewhat laborious to write them, so I'll just suppress this in a second. You think that two events, space-time events, are separated by this in your frame, right? So this could be, for instance, the simultaneous. Simultaneous would mean delta t is 0. Front and back of the length of a pole as it hits the back end of a barn, and that would be 0 and 0, for instance. And I might, in my boosted frame, disagree about whether or not you think those things were separated by delta t equals 0, i.e. they're simultaneous. So I would, because of the nature of this boost, so gamma minus beta gamma, 0, 0, I would disagree about what you think in my frame is simultaneous and what the length of the pole is, for instance. In this particular boost, if we're boosting in the x direction, we would agree on the fact that the pole going into the barn is level, for instance, or it's traveling along what we call the y-axis. But this is how you would use that, is I would pick out an interval, and then we would disagree if I was boosted relative to you. Okay. This is how this looks, written all out in all of its gross expressive glory. This is the nice thing that we've worked for by introducing metrics and introducing Einstein summation notation. Now you can kind of guess why it's called Einstein summation notation, because you got tired of writing all this stuff, is that that equation can be expressed in the following way. So this is your interval for two events. This is my interval. This is the Lorentz transformation that relates your frame to my frame. It could include rotations, but it also includes boosts. So this also lets us express the kinematics of special relativity. And we'll talk about a four velocity, which is the time derivative in your particular frame, or my particular frame, of your the location of your event, the event we're talking about. And in some sense, this is where everything comes from. This is like the Einstein insight about special relativity in a nutshell, is that this is true, is that u squared equals 1, right? No matter what you do, you can run, you can sit on the couch, you can get in a spaceship, you can work as hard as you want to. Your four velocity always has unit norm, right? You're always moving through space-time at a speed of 1. So that's the thing that unites us all. And what this means is, of course, but now that we're enabled with tensor terminology, and we know how to actually take inner products, we need to use a metric. What this really means is eta mu nu, metric tensor, u nu, u mu. Okay, a lot of zeros, a lot of extra work, but it's going to pay off again when we talk a little bit about general relativity. So again, the idea is, you might be sitting on the couch, and that's you in your frame, and I might be moving really fast. Because again, of length contraction, time dilation, it doesn't matter. Your particular four velocity is 1, and the magnitude of my particular forward velocity, no matter how fast I move, is also 1, if you compute it correctly, right? Okay. So all that stuff about throwing out simultaneity, all the physics we won't talk about. I just want to introduce like the mathematical way of expressing this through the metric tensor. So Lorentz transformations, and then also using the metric tensor to talk about intervals itself. Okay, so we'll talk a little bit about the physics of general relativity. And this is something where we actually really need to think about the metric tensor. And we won't have a lot of zeros in it, potentially, or ones. And this is kind of the key insight, which is, I think, much more obvious than the key insight of, I'm moving through space-time with unit forward velocity. It's kind of a clunky way of talking about anything. The key insight of general relativity, in a sense, is that if you believe that stuff moves at finite speed, so I can't transmit information faster than the speed of light, something about gravity just like doesn't quite fly. So you guys learned Newton's law of gravity, which, I've got the sun there, and let's say I've got Halley's Comet, which is probably something around 5 times 10 to the 9th meters away from me. I don't know, yeah, not even kilometers. It's about like 5 light hours or something like that. And this is why Halley's Comet is going in this beautiful Keplerian ellipse. It's being pulled by Newton's law of gravity, which says that g, Newton's constant, times the mass of Halley's Comet times the mass of the sun divided by the distance squared in between them is equal to the force that Halley's Comet experiences. And this is the instantaneous distance. Now, in an elliptical orbit, of course, it changes. It gets closer and farther away, and that's why it speeds up and slows down. Something about this just doesn't fly with the idea of the finite speed of information, namely that information doesn't go faster than the speed of light. So what the sun is doing and what Halley's Comet are doing is they know where each other are. They pull out their pocket calculators. They multiply their mass by the sun's mass, which they know, Newton's constant. And they instantaneously know the distance squared, and then they figure out that's the force that I should experience. Seems really bizarre. So imagine, I think Einstein mostly thought about, had an insight about somebody falling off a ladder and how they felt like they were force-free. But an alternate way of thinking about it is imagine that I wobble the sun. So I go and I grab the sun and I give it a big shake. And what should be true is that shake and that wobble should propagate out and take this 5 light hours to get to Halley's Comet. And that in no way is incorporated into this force of gravity. So that's kind of the key insight. So in fact, what you should think about is space-time is sort of a fabric. The analogy people always come up with is a rubber sheet. But I think you're admitting that you know a lot about the behavior of rubber sheets if you buy into that one. So yeah, imagine that the sun's this big heavy thing and it's kind of warping a sheet. And if I wobble it, ripples in that sheet are going to come out and they're going to travel at the speed of light. Okay, so this is a beautiful idea. The theory behind it is really rough. I'll show you the math at the end of this. But the way that you should express a properly constructed theory of gravity is not through this force law, but rather through the idea that at every point in space, there exists a metric, g mu nu, right? And the metric itself depends on where you are. So I'll just call it x. And what happens is the metric responds to changes in the presence of matter and energy, and warps more or less depending on how much matter or energy is closer or farther to it. So the idea of quote-unquote rubber sheet as space-time can be expressed through a metric, and the metric changes no matter where you are. So let me just write down an example of a metric. So the idea is that we don't do this, we do this. And locally what happens is things respond to the metric that they see. So we express space-time curvature by metrics. And here's an example metric, the Schwarzschild metric. And because it describes spherically symmetric things like planets, stars, and black holes, we'll express it in spherical polar coordinates. And I think there's no t in there, which is right. So this is g mu nu. We're in space-time, so we have a 4x4 box of numbers, tensor. I would do RC squared. Okay, couldn't quite fit that in. Okay, you'll see what we started out with kind of embedded in this is r squared, sine squared theta. So this is just the spatial part of the spherical polar coordinates metric. The new part is this stuff. So this is to the -1 power. So this is the warpage of time and space in response to the presence of a mass. So this is describing a centrally located mass of mass m, and it pulling warping space and time around it. So the way that you would use this is exactly the way that you would use the normal metric that we used for our just normal curvilinear coordinates. If you wanted to compute a vector divergence or a curl or an interval, you would actually use this. The interval that you would be computing is, no, I missed it, yeah, this. So it would be a space-time interval, but this is the thing that you would use, okay? And I will point out something that appeared to Schwarzschild, and you can see immediately in this is that something kind of funny happens here. So I'll rewrite this, it's a little bit small. So these factors here and here, so g00 is equal to -1 minus 2gm over rc squared. And g11 is equal to reciprocal of that thing. Okay. That's the timepiece. That's the radial coordinate. So something about this seems kind of bizarre insofar as the fact that this could vanish and this could vanish. So what I could see is the interval, which I would compute in the usual way. Has what seems to be a pathology in it. So think about computing this. If, for instance, this goes to 0, time stops, or this goes to 0, the distance element goes to infinity. So pretty squirrely. So I gotta write it out, but I'll just write out the first two. Well, if I write out the first two parts, I may as well write out everything. Yeah, let's write it out. So this is me moving a little bit in space-time. And again, I can see that there is the possibility of something really crazy happening when, for instance, we have, we'll call it h naught, the scale factor h for time could go to 0 when this vanishes, or when RC squared equals 2gm. Or let's rewrite it a little bit. Yeah, I think that's reasonable. So there's some constant, and then this is something that looks like the force of gravity, right? So you're really close, or you have a really big mass. And then likewise, h1, the scale factor for r goes to infinity when the same thing is true. So gm over r squared. The thing that looks like the force of gravity, essentially the acceleration due to gravity, is c squared over 2, close to the acceleration of gravity. Okay. See, the idea is that this is possible. I could, pile mass on something, or I could squish something so that it's really close. This is what's called the Schwarzschild radius. So if you keep solving this and solve for r instead, this is the radius at which I compress enough mass to create a black hole. And you can read it directly off of the metric itself. And the real smoking gun work to identify black holes, I think, really started in the 1970s, and it's pretty well established now. So for a while, this was just kind of, an idea like, could you actually do this? Could I compress something so much that I actually blow up the metric and time stops? So that's what a black hole essentially is. So we could solve that to find the Schwarzschild radius. And as an example, the Schwarzschild radius for Earth would be 2 times 6.67 times 10 to the minus 11 units of g. Mass of Earth is like 6.5 or something, 5.97. 5.97 times 10 to the 24th kilograms. And the speed of light is the speed of light. So g is newtons meter squared per kilogram squared. And that turns out to be about 9 millimeters. So if you took the mass of Earth and you compressed it to about the size of, a marble, you would turn us into a black hole. And I think the Schwarzschild radius for the sun is something like 3 kilometers or something like that. There is a supermassive black hole at the center of our galaxy whose Schwarzschild radius is about 40 astronomical units, which is the distance from here to Neptune. So there's quite a lot of mass in there, about 4 million times the mass of the sun. So pretty incredible. Prediction of general relativity basically verified at this point. The question that maybe you have now is, that's pretty cool, and I can interpret metrics because to some degree all the work to understand space-time is done in special relativity. You can ask, where do metrics come from? And what you guys will do is essentially your graduation exercise from tensor stuff is answer part of this question. And I just want to kind of indicate that you shouldn't expect this problem to be easy. Because you're kind of in this self-referential circumstance where mass and energy tell space-time how to curve. But space-time tells mass and energy how to move, right? So the curvature of space-time tells Halley's Comet how to move around the sun. But you know what? Halley's Comet is mass and energy itself. So Halley's Comet warps space-time itself. So space-time tells mass and energy how to move. So to some degree, this is kind of a self-referencing set of equations, and it's pretty complicated, for instance, to actually do dynamics, to talk about how things, for which you would really need to use general relativity to describe work. So for instance, huge computing power goes into numerical relativity to calculate, black holes and neutron stars in spiraling. So super tough, and, to give a sense of that, so it's not just tough because it's self-referential, it's tough because this is kind of complicated. This is the fundamental equation of GR. So these are the field equations. And what I want you guys to get from this is the fact that to some degree you can unravel them. So this is the stress energy tensor, and this is the Einstein curvature tensor. So this is that. Right, so this is space-time curving, and this is the mass and energy. So this really is exactly that. So this is space-time. So this is the curvature, and then this is the this is mass and energy, and they exist in this kind of self-referential environment if you were to actually try to do dynamics with this. And these are the usual things. So this really is Newton's constant. 8 pi is 8 pi, no tricks there, and that's the speed of light. So those are just the usual physics constants. So I'll write this so we don't have to define it again. So you might, we've talked a little bit about what this is. We actually know what it is in 3D. We haven't talked about the space-time component yet, but that's pretty easy. So let me just unravel this so you can see the piece of it that you're going to deal with on the homework. So I might be able to fit this on the rest of the board. So G mu nu is equal to, let me rewrite it in the nice way, R mu nu. And I'm not a particle physicist, so I will put this here. So this is a second rank tensor in 4 dimensions, 3 + 1 dimensions. These are also second rank tensors. This is the cosmological constant if it's on this side, this dark energy if you put it on the other side. Feel free to ask about that. Let me just explain what one of these things are, because you actually know what this is, and that's just kind of a, calculus constant in some sense. So what R mu nu is the contraction of a bigger thing. So that's the Ricci curvature tensor. That's what's called the Riemann tensor, maybe the Riemann curvature tensor. And then that's equal to this ungodly mess. I'll write it and then fill in the indices later because I think I need help with that. Yeah, we definitely need another line for that. And that's the part I know. And then the rest we got to fill in. So that's lambda mu nu nu, lambda mu nu lambda. Then we got to contract over a dummy index, call that beta, lambda. Nope, got to be a lambda. Okay. Then, of course, the next question is, what on earth are these gamma things? So the Christoffel symbols. So the Christoffel symbols, do all downstairs. Beta, mu. Okay, and I don't care if these are illegible because I'll give you the definition or you can look them up. I just want to show you the ridiculous unpacking that goes in. So there's the Einstein curvature tensor. This is the Ricci curvature tensor. That's what's called the Ricci scalar. That's the metric. That's the metric. That's a constant that gets put in called the cosmological constant. And then the Ricci curvature tensor itself is a Riemann curvature tensor, which comes from this other set of antisymmetric mixed derivatives of a thing called the Christoffel symbol, which is a set of near-cyclic permutations of derivatives of the metric. And the point of this is that this is what you have to solve to figure out what the metric is, and embedded in that is the metric itself, right? So, yuck. What you guys will be doing is computing these for given metrics. So that's the little piece that you guys will be learning, but it is the toehold into general relativity itself. So you've seen that at one point in your life, and I'm pretty sure I may have gotten these right. It looks like they're contracting over all the right indices. So that's the idea. If you remember the physics that comes behind it, and you respect the fact that I think it took something like 10 years of work to get the mathematical formalism right, much respect for Einstein and his mathematical collaborators.